Good day, dear conference participants. I want to present our work on the topic Meta-ensemble methods for outlier detection in real estate. Ensemble technology is widely used for many data mining tasks such as classification, clustering, and regression. Many ensemble-based algorithms have been proposed in the scientist literature for three tasks. Compared to clustering, classification, regression problems, ensemble analysis is underrepresented in anomaly detection studies. In some cases, ensemble techniques have been implicitly used by many outlier analysis algorithms, but this approach is often hidden deep in the algorithm, and this is despite the fact that this issue is quite important in the context of outlier analysis. In this paper, a method for constructing ensemble of several ensemble models and multi-level hierarchical ensemble with bypass connections is proposed. The idea of ensemble learning is that by combining strengths of several models, the ensemble can potentially produce better results than any individual model. In this case, the weaker learners can correct each other's mistakes, which in turn lead to the creation of the strongest learner. In any machine learning model, total error is defined as a sum of three components: bias, variance, and interactable error. The optimal balance between bias and depression can be achieved by increasing the amount of data, which allows reducing the impact of random noise in the training sample, using regularization, which limits the complexity of the model and reduces the risk of overfitting, hyperparameter optimization, which allows you to find the best ratio of model complexity and its stability, using the ensemble and meta-ensemble technologies by combining multiple models of ensemble to improve generalization. In machine learning, meta-model and meta-ensemble are related but identical concepts. A meta-model is a high-level model that aggregates the output predictions of base models to give a final prediction. Meta-ensemble is an approach to building multi-level ensembles, i.e., and an ever more complex hierarchy of models. Each sub-ensemble can use its own aggregation mechanism, such as voting, averaging, etc. The final meta-model combines the outputs of these ensembles, providing additional adaptability to the context of the problem. The main differences between these concepts are summarized and presented is table. This work in the next sequential stage in the construction of effective anomaly detection techniques. Our previous research in this area included a comprehensive evaluation of 23 outlier detection algorithms on a real dataset. The analysis used data from the real estate market of Ternopil, in particular the segment of apartment and room sales. The results obtained allow us to single out from the total set the 6 algorithms that provide the highest AUS, ROS, and precision at rank n metrics, optimal execution time, and stability of the obtained results. We will use these algorithms as the basis for building ensembles in the future. According to the results presented in the previous table, the efficiency of outlier detection algorithms is largely determined by the applied data preprocessing methods, in particular categorical feature coding and scaling. Therefore, in the future, depending on the set of data preprocessing methods, we will use 4 groups. Group 1, label encoder, robust scaler. Group 2, label encoder without data scaling. Group 3, one hot encoder, robust scaler. Group 4, one hot encoder without data scaling. The next step is to test the effectiveness of ensemble methods for outlier detection. In our study, ensemble methods from the POD library are used. In general, all ensemble algorithms from this library can be divided into 3 categories according to the number of base learners: algorithms that do not require a base learner to work, algorithms that specify only one base detector, algorithms that allow you to specify a list of base detectors. This figure presents the structure of the Meta-ensemble, which is the facet of the studied one, based on the LSCP algorithms. The blocks display the indication of metrics are intermediate stage of work. The LSCP algorithm used a local approach to improve the accuracy and stability of the ensemble. The principle of its operation is to combine the results of several basic anomaly detection algorithms, taking into account the local context of each point rather than the global one. That is, instead of averaging or weighting across all detectors, LSCP selects the most relevant models for each object based on its local environment. This allows us to take into account different effectiveness of models in different regions of the data space. Architecture of the proposed C-level model is as follows. Level 1 are basis anomaly detection algorithms or their hyperparameterized versions. Level 2 are ensemble techniques, algorithms, or models that combine predictions from several basic first-level detectors, for example, voting, stacking, blending, logistic regression, XGBoost, etc. Level 3 functionally performs the same task as Level 2, but the input can receive both forecast data from Level 2 and directly from Level 1, avoiding the loss of critical information during aggregation. In our study, the LSCP and COOD sample algorithms of the PyOD library are used to aggregate results at Level 2 and 3. These figures present the respectively generalized diagrams of the AUS, ROC, and PN metrics of the studied meta-ensemble. The maximum accuracy indicators of AUC, ROC is 0.932 and PN is 0.679 were provided by the meta-ensemble with bandwidth connections based on the COOD ensemble technique by hierarchically combining the predictions of the optimized ensemble algorithm LODA COOD data of the ensemble of the CBLF and QMCD algorithms, as well as by directly bypassing the results of the optimized algorithm KNN CBLF. Higher detection accuracy is achieved on unscaled datasets using the one-hot encoder categorical feature encoder, which indicates the importance of the correct choice of the data preprocessing method. Conclusions. The proposed system is multi-level and combines individual algorithms, ensemble algorithms that do not require a base linear, and ensemble techniques that combine predictions of several base detectors from PyOD library with the Python programming language. The results of experiments on a real dataset have shown that Meta-ensemble provides higher quality anomaly detection by AUC, ROC, and PN metrics compared to individual models, and classical ensembles reduce the dependence of results on a specific algorithm, demonstrated noise resistance, and high stability of results. The developed approach can be effectively applied in information systems with high error costs. However, it should be taken into account that the need for additional settings, which includes selection of basis algorithms, selection of the ensemble type, the search for optimal hyperparameters, and aggregation method to obtain the final forecast, can complicate the process of developing such informational system. Thank you for your attention.